Welcome everyone. Our speaker today is Vidit Nanda, and he will talk about Harder-Narasimhan filtrations of persistent modules. Take it away.
Thank you very much. I'm very grateful to all the organizers for having me here, and to whoever is attending either live or later on over the internet. So this talk is joint work with Ulrike Tillman, my colleague here at Oxford, and two of our students, Mark and Emil. Emil has recently gotten a job and is working at a big bank, and like I like to tease him, he's doing that Scrooge McDuck dive into his gold coins in a swimming pool in his backyard. Mark is going to be on the market next year. So if you're looking for, if you like this kind of work, you want Mark in your group. Now, this is a very, very strange talk. Usually in a talks, the opening is supposed to be very accessible, very friendly, and then as the talk goes on, people drop out like flies. This is going to be the opposite. You will drop out like flies first, and then I hope people will wake up. So this is sort of an inversion of a talk, if you will. I want to start at a very strange place. I want to start with a little bit of algebraic geometry and representation theory, and I've been obsessed by these two things, but not in spite of TDA, but rather because of TDA. My interest in algebraic geometry and representation theory comes because I love TDA and persistence modules, and I want to understand them better. And I find somehow that these are like my favorite tools, and it's a very good excuse also to learn some very fascinating areas of mathematics, very old, very deep, and surprisingly relevant to the sorts of things that you and I might care about on a daily basis. So let me start with like the first basic idea in this talk. It's called semi-stability, and I would not expect you to have seen it, which is why this is the worst way to begin a talk. This is not how we're supposed to gently lead people into the deep end of the pool. So we start with algebraic geometry, which is the study of algebraic variety. So an algebraic variety for our purposes here, you take a field. For us, it'll always be the real or complex numbers, and then you look at polynomials over that field, and wherever that polynomial vanishes, you get, that's an algebraic variety. So the picture over here has this degree 8 polynomial associated with it. It's a very pretty picture. And so this is the zero set in R2 of this polynomial. So one of the few things you start to notice immediately is they tend to have singularities. They're not always sort of nice manifolds. Even so, their singularities are not so bad in general. They always have these nice stratifications and so on. Anyway, that's not the point. It's just, it's a way to generate geometry from algebra. You take a polynomial set at equal to 0, and behold, the picture pops out. And then you can ask all sorts of interesting questions about this picture. Now, if you look at this picture, it's extremely symmetric. You will notice certain discrete symmetries of it. But in general, because these are smooth objects, they have Lie groups worth of symmetries. So let X be such an algebraic variety, and let's pretend that there is a subgroup of GLNF, so n by n invertible matrices, which acts in some interesting way on X. And the questions that the notion of semi-stability and all of that wants to answer is, how do we understand, how do we study, how can we make sense of the quotient X mod G? Now, if I hear something is generated by a polynomial, and I know that there's a matrix that's acting on these variables x1 through xn, one natural thing to look at is to hope that X mod G, this quotient, is itself an algebraic variety, and it's the variety. You take all the polynomials that generate your original X, and you look at the ones that are left invariant by this group action. So these are the invariant polynomials, and you pray to God that this variety is the quotient. Like that would be what the first guess would be, right? You have these polynomials, they don't care about symmetry. Now you insert some symmetry, and you hope that the symmetric polynomials, the ones that respect your symmetry, are precisely the ones that generate the quotient. And now, if you take that idea and try to sort of, what's the easiest example of such a thing that you could build, you immediately run up into some exciting difficulties. So if you let the multiplicative real numbers act on the standard Euclidean plane by lambda takes the X variable and scales it, and then you do 1 over lambda of the Y variable. So basically the product is preserved, but you're scaling the first variable up by lambda and sort of diminishing the second variable by lambda, if you like. I guess I've assumed lambda is bigger than 1, but it works the other way if lambda is smaller than 1. So what are the invariant polynomials? It doesn't take very long to figure out that the ring of polynomials generated by basically x, y, you smoosh the x and y together, and that remains invariant to this. In fact, that's the only thing that remains. It's very easy to check that this remains invariant. It takes a little bit more work to say that if it's not a polynomial in x, y, then it won't be invariant under this transformation, but you can do it. What goes wrong with this is if I set x, y equals 1, let's say, then I get this, maybe the orange looking line that's going in the positive quadrant in the picture I've drawn. Maybe you're seeing it like this. So that's the way I should be doing it. And so this very nicely splits up, and these are all orbits, right? If you look at this group action, this is a single orbit of that group passing through, let's say 1, 1, will be the point x, y equals 1. And similarly, there's sort of a reflected point on the other side where x, y equals -1. That's also drawn in orange. And then you can imagine there's sort of a foliation of the positive and the negative quadrant. And it's working really well. If I set x, y equals blah, I get the orbit through blah. It's separating my quotient space really, really nicely. I get one sort of orbit per value of x, y. And then it dies when I set x, y equals 0. The reason for that is there are 3 orbits. There's the origin that's fixed, right? If I take 0, 0, and I apply this group action, lambda times 0 and 1 over lambda times 0, it stays there. It doesn't move. It has a very fat stabilizer. Everything stabilizes that. And for similar reasons, the x and y axis are also just scaled up and down. You'll never fly out of the x-axis, the positive or negative x-axis, by applying these transformations. So somehow these the quotient is not what you sort of geometrically want it to be. These orbits get crushed to a single point in the quotient corresponding to x, y equals 0. And this is the sort of starting point of a deep area of mathematics called geometric invariant theory. We want to study these invariant polynomials while keeping in our hearts the knowledge that these things they're not the faithful quotient that you might want. So when you have a situation where things don't work out the way you really wanted in the beginning, there are sort of 2 options. Either you find a bigger hammer or you throw out the stuff that's inconvenient. And so I think you should do both in general, but here one has to sort of find what the good and bad areas are and what's sort of the differentiator. How do I know an orbit will be separated by these invariant polynomials and how it won't? And this example is actually very, very illustrative, but from this example, I hope you won't mind if I make the definition that a point x on the variety is semi-stable if the orbit is relatively open, it should say in x, and contains the origin and its closure. So the axes minus the origin, those 2 are semi-stable. They're somehow different. That's where the theory of invariant polynomials seems to break when it comes to constructing a natural quotient of this group action on the variety. Okay. All right, so let's just take this idea and store it somewhere in your brain. I've deliberately been as slow through the slide as possible so that if you're trying to follow along live, you haven't missed anything. But now let's move on to something different. This is the basic, from semi-stability, you can sort of bootstrap a theory of understanding group actions on complicated algebraic varieties. And I'll give you an example of vector bundles here. Just because that was the first place where this occurred. So in some sense, this is the most natural example to look at. So I let pi be a holomorphic vector bundle over a smooth one-dimensional complex projective variety. Okay, that's a lot of annoying words, but let's see. I'll get to holomorphic vector bundle later. First, let's define what X is. It's a one-dimensional complex projective variety, which means that, okay, its total dimension, I mean, it might have singularities, but the top bit of it has dimension 1. So it's a one-dimensional complex space. Projective just means that the defining polynomials are all homogeneous. They have the same degree D, right? So, okay. So that's a one-dimensional complex projective variety. And a vector bundle is something that assigns to each point of this variety a vector in C, basically a complex number. And to be holomorphic, there's a standard smooth structure on these vector bundles, and the projection map pi has to be holomorphic in the standard one-dimensional complex analysis sense. So Cauchy-Riemann equations. Okay, let's say you have something like this. The rank of E is a dimension of a fiber. And because it's a vector bundle, the dimension of the fiber doesn't change. The fiber can change, but its dimension is the same. Everything's as long as things are connected, which I guess I didn't say. And okay, and there's a similar way of defining the degree. So the degree of a variety is obtained as follows. You take this object and you slice it with a hyperplane that cuts its dimension by 1, slice it with another hyperplane, it cuts its dimension by 2, slice it with as many hyperplanes as the dimension of the variety, and then you've reduced it to some number of points. Now, it's a miracle of complex projective geometry that this number of points almost doesn't depend on what hyperplanes you use. So that number is the degree. So there's that number. Okay, what's interesting about rank and degree is that both of them are additive across short exact sequences. So let's just believe me for a second that it makes sense to define short exact sequences of vector bundles. It's actually not so bad. You just get short exact sequences of one-dimensional complex vector spaces or something. Anyway, so given a short exact sequence of vector bundles, both rank and degree have the additive property that if you take the ranks of the two outside parts and add them up, you get the rank of the middle, and similarly for the degree. Okay, now you define the bundle to be semi-stable if for every non-zero subbundle, we have the ratio of degree of rank of the smaller vector bundle is less than the ratio of degree to rank of the bigger vector bundle. This definition comes from looking at these holomorphic vector bundles as a variety in the previous sense, applying the previous definition, chasing it all the way down. And this is the it's a much simpler thing because this is a much simpler setting than, an arbitrary group acting on an arbitrary variety. So this is a very sort of almost numerical looking criterion for semi-stability. And this is the beginning of Harder-Narasimhan theory. So every vector bundle of the type described over X, of finite rank and degree, has the unique filtration, 0 going to E1 going to E2 all the way up to EK, so that the successive quotients are all semi-stable in the sense defined above. So if you take the vector EI quotient EI minus 1 and look at a sub-object of that has strictly smaller slope, where slope is defined as not strictly smaller, weakly smaller slope, where slope is defined as the ratio of degree to rank. And moreover, these quotients, as you move from left to right, E0 over E1 has a bigger slope than E1 over E2 has a bigger slope than E. Okay, so this is a way to take any vector bundle on the planet and chop it up, build a filtration. Okay, I don't understand the pieces of the filtration, but if we pretend that semi-stable things are nice, then every quotient is semi-stable, and I have some control over these slopes. They're decreasing as I go from left to right and look at the successive quotients. Okay, so this was the story for vector bundles. I don't really care so much about vector bundles, so let's get a little bit more general, and then this sort of framework, like an amoeba, will sort of surround the things we care about, and then we can start applying it to the things we actually care about. So let funny A be a small abelian category, and then remember that its growth indeed group is the abelian group. Remember, or learn very quickly, that K of A is the abelian group generated by all the objects, subject to the relation that V equals U plus W for each exact sequence, short exact sequence, 0 to U to V to W. This is exactly the additive property that we're just sort of formalizing what an additive object is by giving them a domain. So an additive object on A is anything that factors through this growth indeed group. It forces you, if you fit in a short exact sequence, the outside terms, their sum had better give you whatever you assign to the inside term. And now we define a central charge on this category to be any abelian group homomorphism from the growth indeed group of the category to the additive complex numbers that sends non-zero objects to the right half plane. So here's a picture. Whenever I have 0 to U to V to W exact, I will get some vector for U, some vector for W, and their sum by the parallelogram law has to give me the vector for V. That's what it means to factor through the growth indeed group. And now you can define the slope.
Interrupt you?
Sure.
Sorry, we have a question in the chat that I wanted to quickly ask. Namely, Nicole Sanderson is asking, how did the degree definition incorporate E and E prime?
How did the
Maybe it helps
degree
you.
definition? All right, let's go back. Can I go back? How did the degree definition incorporate E and E prime? So I mean, hopefully the equation there tells you. So E prime has a degree that is not necessarily smaller than the degree of E. You can have a subvariety of a big variety whose degree is larger. So it's not true that the degree is like sort of an increasing with filtration or something like that. And then it is true that the rank is increasing with filtration. But then when you look at this numerator over the denominator, the question is, did the degree increase enough to keep up with the rank or not? So it's a very non-trivial, to me, ratio to understand. And it's not true that E prime's degree will have to be smaller than the degree of E. And in fact, that's the whole point, that it's not true for an arbitrary E prime that this ratio is less. It's only true for the semi-stable ones. I hope this answers the question. If not, I'm happy to say more.
I think it does answer the question. Thank you.
You know, I guess I thought that the degree definition was about splitting up X with hyperplanes, and maybe I missed how E came into, like,
well, so yeah, so
and then how did E come in?
I've gone out of my way to not define the degree of a vector bundle. We can talk about it later if you'd like.
Okay.
It would not let me finish in the recommended time if I.
No, that's fine. I think just understanding that it could go up when prime goes down.
I mean, I think
helpful,
the
at least
easiest example to keep in mind is just look at a sphere, like sitting in two-dimensional space. Its degree is always 2. You cut it with a hyperplane that actually goes through, you get a circle. You take a circle and cut it with another hyperplane, you have 2 points, right? The degree of a sphere is 2. Any subvariety of the sphere is now allowed, and you can easily imagine a twisty curve on the sphere, which if you cut with a hyperplane, you get 50 points. So that's an easy example to show that the degree doesn't have to sort of go up with the with inclusions, basically.
Perfect, thank you.
Great. Moving on, said that. Okay, so we define the slope as basically exactly what you want. So it should really be the angle, but I'm only going to care about comparison, and arctan is nice and monotone. So instead of arctanning this slope, I'm just going to leave it as a ratio of imaginary part to real part. And now you define an object to be semi-stable if, with respect to this central charge phi, if the slope of every non-trivial sub-object is less than or equal to the slope of the big object. So the big object is semi-stable if V is semi-stable if the slope of every U is less than or equal to the slope of V. So now these two imaginary and real parts are playing the role of rank and degree, right? That those ratios have to be monotone for semi-stability to hold. And now these two things are just playing that role in a category where we may not have degrees or ranks. We just have a function from the growth and decay of the category to the additive complex number. So now obviously this depends on phi. So one choice of phi for vector bundles would have been degree over rank. But there are several. So now you have various lenses along which you can be semi-stable or not. So this is work of Rudakov that this Harder-Narasimhan filtration works in this setting, provided that the abelian category you started with is both Artinian and Noetherian. So then you get this property that there's a unique filtration where each successive quotient is semi-stable and they have strictly decreasing slopes. Now, if you don't know what Artinian and Noetherian means, I never remember which is which, but thankfully we need both. So I can tell you what the union of them means. One of them means that if you take an object and you keep getting, if you keep looking at all the sub-objects of that, eventually that stabilizes. And the other one means if you take an object and keep looking at all successive portions of that, eventually that sequence stabilizes. So that's what Artinian and Noetherian mean for. So you keep looking at injective maps to the left or surjective maps to the right, eventually you have to go to 0 or something like that. That's any such sequence has to stabilize up to isomorphism. Okay, good. So that's the story. Now, you could do this with any category you like, and you could do this with any such central chart. So you have to take a category, think about what its growth and decay group should be, and look at group homomorphisms to the complex plane. And each one of those gives you a new theory of semi-stability. The most boring one is the one where you keep the real part at some constant, let's say 1, and you make all the fees the same, 0. Everything works, right? Everything lives on the real line because everything has 0 imaginary part. And you can get a theory of semi-stability, but it's just terrible. The Harder-Narasimhan filtration is just one step. Everything is semi-stable, and by uniqueness, 0 to V is semi-stable and has whatever slope it has. And that's the end of the story. Every sub-object has the same slope. So that's the most boring case. If I make phi just be 1 plus I, like 1 plus 0 I, basically that. Okay, let's keep going.
Interrupt you again?
Yes, yes.
And later you use the notation HN filtration, I guess Harder-Narasimhan filtration, but did you actually define what it is, or did the person asking the question just miss it?
I've defined it by the property that such a thing exists and it's unique. I haven't told you how to find it. Okay. Right, there's only one such thing, and that one is the one I'll call a Harder-Narasimhan filtration. It's not a helpful definition at the moment, but we'll see some more helpful incarnations of it. Thank you. That's a very fair question. But it's just one of those things that's defined by axiom. And so you really have to sort of get your hands dirty to get a few examples. And we will do that. I just didn't want to start with like messy calculations. Okay, let's get to the part that's now coming slightly closer to TDA. Sorry, we were too far at the deep end, and now we'll sort of waddle our way to the middle of the pool. One of the favorite sort of choices of abelian category I could have is representation of a fixed finite quiver. And so in this case, we will consider central charges on the category of representations of a quiver, and always valued in finite dimensional F vector spaces. Do I have some favorite quivers to think about? Yes, I do. It's that one with sort of arbitrary length. I really like that one. That gives me ordinary persistence modules. I like the one also where some of the arrows in the middle might go the other way. So that gives me zigzag persistence modules. So type A is what these are called. I really like them because much of the one-dimensional theory of persistence is about, all of it, you could argue, is about these quiver representations. The other kind I kind of like are these ladders. There have been a few papers in TDA focusing on ladders. That's not why I love them so much. I love them because a ladder quiver represents morphisms of ordinary persistence modules. Right? This is a morphism from the top persistence module to the bottom persistence module. And if I learn something about representations of these quivers, maybe I can say something about classifying morphisms of persistence modules. So that's pretty nice. And obviously the one everyone loves and cares about the most, if you're working at the theoretical end of TDA, are these sort of 2 or 3 or 4 parameters or multi-parameter persistence modules. I've drawn the case of 2 parameters here. I refuse to draw higher ones, but let's pretend that there's cubes and hypercubes and mega hypercubes of these all the way, turtles all the way up. Okay, so let's say we have a representation of a quiver, and these are the types of quivers I want you to keep in mind, not sort of arbitrary crazy ones. Then the dimension vector of that representation is the map that assigns to each vertex a dimension of the vector space that lives over that vertex. And this turns out to be an abelian group homomorphism from the Grothendieck group to the set of functions from the vertices to the integers. And when Q has no directed cycle, this is in fact an isomorphism. So it takes a little bit of work to show, but basically the Grothendieck group that was so mysterious in the previous slide is now just generated by functions from the vertices to the integers. So that's pretty nice. And all the quivers we will care about in TDA happen to be acyclic. There are no directed loops, so that's pretty good. So this isomorphism property will hold for everything I say around. And central charges which factor through this dimension homomorphism are basically giving you a complex number, beta x plus I alpha x, for each vertex x. And beta x has to be, the real part has to be, remember, the right half plane. So that has to be strictly positive. So it's just standard to set beta x equals 1 and reduce all the sort of thinking we have to do about the imaginary component. So how high will it go? Everything will live on the line, on the real axis equals 1. We could have made it 1/2 and played some games with, or with the Riemann hypothesis or something, but we did not do that. So everything's going to sort of normalize to 1. Okay. All right. So here's a definition. If I have a central charge, which is just, again, assigning a single complex number, or real number rather, to every vertex, the alpha slope of a non-zero representation is that ratio. You take the alpha weighted combinations of the dimensions and divide it by the total dimensions. That's it. And remember that semi-stability still works the same way. V is semi-stable a lot with respect to alpha if for every non-zero subrepresentation you have that equality that's there. That the slope of the subrepresentation has to be smaller than the slope of the big representation. Okay.
Sorry,
so
someone in the chat asks, excuse me, what is Q0 again?
Q0 is the set of vertices. Did I not say that? Yeah, okay, so dimension vector. So okay, so Q0 is a set of all vertices of the quiver. The dots and not the arrows. Yes, okay, good. All right. So now we get to the sort of invariant we want. You could take a central charge, fix it, and the minute you fix that central charge, the theorem of Rudakov applies. And so the map that assigns to each vertex the vector of dimensions of the first quotient, the second quotient, the third quotient, all the way up to the end. So remember, these were the semi-stable objects. You sort of had a filtration, and S1 was the ratio V1 to V2 and so on all the way up. Sorry, V1 to V0 and so on all the way up. So the dimension vectors of those quotients, this combinatorial object, it sends each vertex to a vector of integers. That's it. This is called the Harder-Narasimhan type along alpha. Again, I haven't told you how to compute anything, but let's pretend that you could have access to this unique filtration that satisfied these two properties. Then this would be the invariant that you would assign to each vertex, the vector that you'd assign to each vertex. Now, it's purely combinatorial, and the whole thing depends on how nice alpha is. If I set alpha equals 0, then all of the Harder-Narasimhan filtration collapses to one step, as I said before, and then you will just get the dimension vector of V, which is an invariant of something. I mean, it's certainly an invariant of a representation to give you back the dimension. It's not very informative because it loses information of sort of all the maps. Okay, so what do we really want? What would be really, really nice is if this invariant was complete. That is, if from these dimension vectors, for maybe finitely many choices of alpha, I could tell you the full sort of barcode decomposition whenever such a thing existed. That would be nice. So what do we use to get this? I know no combinatorial invariant is going to be complete on like the full multi-parameter persistence models, but the part we really need is that if alpha is complete on some subcategory of the category of representations of the quiver, then every indecomposable must be alpha stable. So this is something you can prove by looking at short exact sequences and using additivity. So I'm not going to tell you how to prove this. It is in the paper. It's not very complicated, but this is the tool. So now you take your category of persistence modules that you care about. This is the game. This is the yoga. And you have to sort of find the alpha that makes as many of the indecomposables you care about semi-stable in this sense. So what does it take? You look at the indecomposables, you look at the the sub representations of those, and then you really want those to have a smaller alpha slope than of the indecomposable itself, right? So there are two goals. The first, I'm just going to say some general results about these Harder-Narasimhan things with very simple choices of alpha, and then we'll really get into the persistent stuff. I promise. There's one more definition, and then I'll show you what all of this is good for. So the definition I want is that of the skyscraper invariant. So when I'm trying to choose an alpha, I need a real number for every vertex, and sort of this is a vector space. It comes with a very sort of natural choice of bases, which is the delta function at each vertex. Linear combinations of these will generate everything. So I want to look at these basis elements. So I'll just call them delta x to make you think of delta functions. So it assigns 1 to the vertex X and 0 to everything else. And then this collection, so there's only finitely many of these because there's finitely many vertices in my quiver. So I look at the central charge that makes that one 1 and everything else 0. And this is called the skyscraper invariant. So I'm just going to tell you what this skyscraper invariant can tell you about a quiver representation. And just to be absolutely clear, since this assigns 0 away from the vertex that's in the middle, so X, the delta X. So the slope of any representation is a dimension of Vx divided by the total dimension of the quiver representation V. So now here's the game. This is what I want you to think about. You have a representation V, and you assign to it this number. There's a dimension of Vx, where X is some chosen vertex, divided by the total dimension of that representation, out of all of the dimensions of all the different pieces, at all the different vertices. Each sub-representation will get a similar number, right? Dimension of Ux divided by the sum of dimensions of Uys. And now the question is, if my V was an indecomposable, can I make sure that all sub-objects U have a smaller number than this one? That's it. That's the only game. So there is a representation that sort of pops out of this because of the sort of asymmetry of Vx, right? So at the top, we only let Vx survive. At the bottom, everything survives. So this is very sort of, it treats X very special. So the spanning subrepresentation of V at X is the intersection of all subrepresentations where Ux is isomorphic to V. Now, this might sound strange, but really, this is what I want you to think about. You look at your quiver representation, you go to your vertex X, and there's a vector space, right? That your quiver representation assigned there. Take that vector space and flow it out using all the available maps to the rest of the quiver. Right? Just take that vector space, map it this way, map it that way, map it everywhere in your quiver. And you get some subrepresentation, and that's the spanning subrepresentation. These are, if you think about these things sort of from a homological algebra perspective, these are called like the free objects in the category, basically. So people try to come up with, the picture looks like this. So everything is filled over here, and then 0 to the left of the cone. So this cone point would be X in this case. So Vx would just be sort of spreading out from vertex X if you had a 2-parameter persistence module. Okay, so the rank invariant of Zomerodian and Carlson, which is sort of the first discrete invariant for multi-parameter persistence modules, is given by assigning to every pair of vertices X and Y the dimension at Y of the spread representation Vx. So if Y is less than X in the partial order, this is 0. If Y is bigger than X, then some part of X reaches Y, and that the dimension of whatever reaches Y is that's the rank invariant. That's what the rank invariant assigns to that interval from X to Y. So here's the first theorem. Finally, after all this nonsense, the theorem, you can actually recover the rank invariant explicitly from the skyscraper invariant. In fact, if you want to get rho V of XY, it's enough to know the skyscraper with respect to delta X. That'll tell you all the Y's above the X. So there's a nice formula there that'll do it. And what does the proof amount to? It amounts to proving, and this is not easy, that the Harder-Narasimhan filtration along delta X satisfies the property that the ith step is the same whether you look at the whole representation or the spanning representation. So how do I say this? So the penultimate one, just before you go to the full one, you get the spanning subrepresentation. That's what I want to say. So the Harder-Narasimhan is blah, 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 and then the spanning representation X, and then the full thing V. And that's what makes this proof work. Now, I know what you're thinking. Here's a crazy looking person using crazy looking tools to come up with another invariant for multi-parameter persistence modules. I know how this feels. I don't use a Mac because of this picture. I feel like their fastest growing product category is dongles. There's never any ports in the damn things. And now what's the fastest growing category of TDA after, let's say, vectorizations? It's invariants for multi-parameter persistence modules. They just spread like crazy. There's so many of them. I've only put 4 of them up here, but everyone and their uncle is coming up with a new invariant for multi-parameter persistence modules. So you sort of have to sort of decide why you're doing this. I'm doing this because I think that multi-parameter persistence modules are very naturally algebraic varieties. Anyway, so the space of all multi-parameter persistence modules with fixed dimension vectors is immediately an algebraic variety. So, and the natural GL action on that algebraic variety puts you very much in the setting of geometric invariant theory, which is why I'm using tools from geometric invariant theory. Okay, so what are these good for? So let's baby steps. For ordinary persistence modules, which are representations of type A quivers, what can we say about them? We can say that the rank invariant is complete, so this skyscraper invariant is good too, but we can do much better than the skyscraper invariant. So we know that any reasonable persistence module decomposes a direct sum of interval modules, and all we need is to recover the multiplicity of these AB intervals, and then we know the full barcode, and therefore we know everything. So here's a nice theorem. You remember we're supposed to assign numbers to vertices. As long as your numbers are strictly decreasing from left to right, a single central charge with that property is complete. So if you give me that central charge, the Harder-Narasimhan filtration along that will recover all of the bars. How does this work? Well, so the Harder-Narasimhan filtration will have, say, n steps. 0 to 1, that quotient, that tells me everything about bars of length, bars going from 0 to 1. Then 1 to 2 will tell me everything about bars going from 0 to 2, and so on. Like, it sorts them alphabetically. It's very nice, like lexicographically, and the various steps of the Harder-Narasimhan filtration just produce the barcode decomposition. It's very nice. And in fact, what's nice is that you can do the same thing for zigzag persistence modules, but then it's not strictly decreasing. It depends on which arrows go left and right. There's a different partial order depending, and I really don't want to get into the combinatorics of it. So that's the first result. So on zigzag and these ordinary persistence modules, you don't need anything as fancy as the skyscraper invariant. Anything that sort of basically decreases along the edges will work. For multi-parameter persistence modules, which are like sort of representations of these grid quivers where every possible square commutes, we again know that the rank invariant can be recovered from the skyscraper invariant. That's a purely general result. And we know that the rank invariant is complete on the rectangle decomposable modules. And we can do much better than that, which is to say that if you let H be the collection of central charges where 2 different rectangles have the same slope, and this is sort of codimension 1 or worse in the space of all maps from the vertices to R. A central charge which lies outside of H is complete on the rectangle decomposable ones. Sorry, that should be RD instead of rec. I changed notation in the middle of making the slide, but it's complete if and only if, again, you have this property where you decrease along the edges. And what's happening here is that basically all of the sub-representations of a rectangle are basically going to be things that have to move up or to the right. Right? That's how you're going to get a sub-representation. If I have a rectangle like that's going off into space, all the sub-representations can live here or they can live further up or to the right. And forcing this to decrease along the edges forces that thing to have a smaller slope than the first one. It's sort of very sort of viscerally geometric, but you want to write it down, you have to work with this hyperplane of inequalities. And this leads to some absolutely fancy combinatorics. And I dare you to prove this without looking at the paper. If I have X and Y, arbitrary non-empty subsets of a finite distributive lattice, then the product of their cardinalities has to be smaller than or equal to the product of the cardinalities of their join and meet. Like, just try it. This is the type of combinatorics that goes into proving theorem C above. And if you want to get fancier and try to use more central charges than a single one, then the list of these inequalities just gets really, really annoying. And if you use a category that's not representation finite, then you find a certificate. Like, you'll get like 5 inequalities and you cannot possibly satisfy all of them. So then you know that no finite set of central charges is complete. Okay, let me end with just a little bit about ladder persistence modules. So it's one of these. Yeah, go ahead.
Again, a question from the chat. I think probably you kind of already answered it in the sense that the question was whether the theorem on the last slide was only for one ordinary one-parameter persistent homology. But
and zigzag,
yes,
but I didn't put down the zigzag.
Yeah,
The
and then the
zigzag
theorem
one's in the paper. Yeah, and
then this slide is about
ordinary one is a
multi-parameters.
special case. Yeah, this is multi-parameter. Okay. Okay, next one is ladder persistence modules. And we know that when the length of the ladder, which I'll call L here, is bigger than 3, that they're not representation finite, but of course we can restrict to the interval decomposable ones, the ones that like by fiat decompose into like these direct sums of intervals. And here's the theorem for those. No single central charge can be complete. You can write down the necessary inequalities and no single alpha will do it. But there is a finite collection of central charges, which is basically cubic in the length of the ladder that is complete. So if you know the Harder-Narasimhan filtration along those finitely many, and we've written them down explicitly in the paper, I just don't want to sort of create like a very messy slide here. That is complete. So you can get every interval that appears and with what multiplicity from the Harder-Narasimhan filtration along these finitely many central charges. And again, this is explicitly described. And what I like about it is that there are at most 2 skyscrapers that have to be linearly combined. So remember, an arbitrary central charge is any old combination of these skyscrapers because the skyscrapers form a basis. But here, there's only going to be 2 vertices at which it's supported somewhere here. So some finite subset of pairs of vertices does the job. And the proof strategy works for multi-parameter persistence modules, which admit a decomposition into intervals with at most 2 sources. So things that look like zag and then everything up there. Okay, so that's it. The paper is on archive and you can see it there. And it will appear in the Transactions of the London Math Society. So please check it out and feel free to ask any questions. Thank you for your patience. It was very good to talk to all of you today.
Hey, thank you very much. This was a very nice talk. And let's please all unmute yourself so that we can clap together. Great, and we can go to the question part. Who has the first question? Maybe I'll start with one question while the other people are still thinking. Somehow about what you said, that you don't just want to add one more invariant of persistence modules. I missed a bit the part, like, so why in the end did you then decide to add another invariant? What is now the thing that you can measure that other people can't measure? Or
so okay, so there are a couple of reasons to do this. Basically there are things that I find without sort of taking anything away from the work that people have done so far. I feel like broadly the invariants that are out there can be classified into 2 broad groups. The first one is these homological invariants. You treat it as an object in an abelian category, do a resolution of some sort, injective, free, minimal, whatever, and then look at the Betty numbers of that injective resolution. And that's sort of one or some other property of that resolution or those resolutions in some equivalence class. So that's one. And the other ones are these Mobius inversion-based invariants that come from these limit to co-limit maps of sub-quivers or sub-diagrams. Both of these are sort of very, very married to the sorts of quivers that we see in general, which is like this acyclic 2 or n parameter quiver going by. We don't really understand free resolutions so well of arbitrary quiver representations. Now, if you take a step back and think about the settings in which persistence has been really, really useful, one of my favorite examples is circular coordinates, which sort of, what sort of quiver representation would represent circular coordinates? Well, if you really think about it, you don't have this nice partial order anymore. There's no like beginning and end, there's no poset structure anymore. So when people define persistence modules as functors out of posets, which is basically the setting of both these classes of invariants, they're excluding this very important category of things that are not partially ordered, but you still want to do persistence along. So if you're being honest, the circular coordinates thing, if you have, you know, two circular coordinates, your persistence module is living on a torus. There's a circle going this way, there's a circle going that way, and you have, like, let's say you discretize it, and you have like this quiver with all sorts of interesting cycles living on a torus. And there I find all the existing tools fail. I don't have this nice poset, and I don't have a functor from a poset to an abelian category, and I cannot use any of the existing machinery in like a way that I understand. This thing doesn't care. It will give you an invariant, whether you like it or not, but it sort of extends to that setting that I really like of not being married to a partial order or like these increasing directions. So that's the 2-minute spiel for why I did this.
Thank you. That's a great answer. Georg Essel?
Okay, it's very dark, a fascinating talk, and by the way, thank you so much for what you just said, because basically that's where my question is. So I work with time series data, audio, and periodicity is one of our main interests. That's what we care about, and that's the circle you just mentioned, right? So we run around circles in my field. And my question is just a question of pure ignorance, because like when I followed your talk, I was constantly thinking about this. And you mentioned that you were working on acyclic quivers. I can sort of see a fix for zigzag persistence where you close those, but can you explain a little more how you...
No.
Yeah.
There's a difference. So everything I've said, almost everything I've said, like I mean, there were some specific results for the persistency quivers, the three families, the ordinary and the multi-parameter in this grid, and the ladder persistence modules. So those results, I do assume the structure of the quiver, but the initial part where you can recover the ranks of various pieces, all of that works sort of in general. Now, what I do want to say is I did not assume acyclic. Acyclic only helps me figure out the growth ND group, which is to say that there's a map from the growth ND group to the set of functions from the vertices, and that would give me everything, all the possible central charges, if the quiver was acyclic. And it's not complete. Like it does, there are things beyond the ones I can get from functions on the vertices in the case where the quiver is not acyclic. But I haven't made any claims. The skyscraper, where you could always put a skyscraper in any one vertex without caring about the cycles and get an invariant out.
Interesting.
So,
yeah.
so the acyclicity doesn't bother you. What is harder to determine in those cases what the sub-objects are. It's really hard to figure because you get these basically, if it was like a single vertex and a single map, then the sub-objects would have to care about the like one eigenspace of that linear map.
Right.
Because you So
which is precisely what I want. So in my world, that's awesome. Like I want exactly these eigenspaces. Fascinating. I'm gonna have to look at the paper, but maybe I can shoot you an email and
anytime. This is true for anyone. You don't have to ask to send me an email. That's the point of email. It's great. You can just send it to people. So
this is great, and I'm very interested in this very direction. So thank you so much for this work. Fascinating. Thank you.
You're most welcome. Cheers.
And I saw that while we were talking, there was a comment by Ezra Miller saying, as long as the poset is finite. So I guess everything that you said only works for finite posets?
Yes, but Mark the sequel, literally Mark. Mark has a paper out, a subsequent paper with the same title but stability in it that just went up like a month ago, where he establishes that the Harder-Narasimhan invariant under certain reasonable conditions is stable if you look at these just tame modules on the line. So there's no finiteness, but there's so we're using tame, which means essentially we can reduce it to a finite situation. By the way, hi Ezra, sorry I can't see you, but we can talk more about this. But if you look at Mark's last paper, you will see the first example of this actually in a non-finite setting.
Nice. Okay, any more questions? Yeah, Ezra, right, thanks. Any more questions? Okay, then if not, maybe I'll end the recording here and people can still ask questions afterwards. Thank you again. It was a great talk.
Thank you.